Okay, recording. So, new chapter for today. We're starting with chapter 7. So we're going to start off by talking about surfaces. And the reason for this is going to be kind of the context for the entire conversation that's going to happen in chapter 7. Well, pretty much. In R3, when you're talking about things in R3 and line integrals and things like that, it turns out that integrals over surfaces are also a really natural thing to talk about. So in order to be able to define integrals on surfaces, we're going to have to be able to parameterize surfaces. And this shouldn't be too big of a shock. If you think about it, that's how we define integrals on curves, right? We define integrals on curves by saying, well, I can view them as an image by a parameterization. We can pull back through that parameterization, and then off we go. Morally, we're going to do the same thing now with surfaces. Okay, so starting with the idea of a parametric surface. Parametric surface it's really exactly what you would expect. It is a function that gives position as a function of two parameters. It's a ripoff of the idea of a parametric curve, which gives position as a function of one parameter. Right? So here's an easy first example. In fact, we've seen this before. If you go back to section 1.5, this is in there. It's also, by the way, an exercise, or something closely related to this was an exercise in that, I believe, that same section. So hopefully this will look familiar. If not, you can flash back to that previous work. And the idea is that if you have a vector given that's parallel to the plane you want to parameterize, and another vector parallel to the plane that you want to parameterize. And then let's say some starting point. Any point in the plane, doesn't matter. And you can think of that as a point, you can think of it by its position vector, take your pick, doesn't matter. Okay, well, starting with that point in the plane, notice that if you take a scalar multiple of that first direction vector, that too is parallel to the plane, which when you then add to your original point x naught, moving from in the plane parallel to the plane keeps you still in the plane. Right? And then likewise, a scalar multiple of the second direction vector, right? Again, still keeps you in the plane. So you start in the plane, you move parallel to the plane, then you remain in the plane. And furthermore, notice that by the choice of these parameters, S and T, right? S and T from are the inputs to this function. Depending on what S and T you pick, that just controls, well, how far do you move in the one direction, how far do you move in the other direction, and you can choose those parameters to be whatever you want, of course. They are input parameters, they can do whatever you want, and so you can move basically anywhere in the plane. As a result, then, over all values of S and T, this sort of sweeps out the entire plane. Okay, so I hope this is a reasonable idea, and this the function that we end up with here, this function here, we call this a parameterization of the plane. Okay, all right. So that's a first example. Now I've got a bunch of other examples. Getting ahead of myself. Real quick observation. Thinking back to parametric curves. The input to the parameterization is any input parameter. You can think of it however you want. You can call it whatever you want. But it's very convenient to think of it as being time, right? To think of position as a function of time, because then we get the geometric and kind of physical metaphor of a particle moving through space, and we can sort of latch on to this physical intuition that we have for movement to get some sense for that parameterization. Well, the problem is we now have two parameters, and of course there is no such thing as two simultaneous independent notions of time, right? Depending on what science fiction movie is your favorite, it's not really a standard thing, right? Without getting into too much metaphysics, for example, not really a reasonable concept, not a standard concept. So try not to think of the parameters as being time, right? But that said, they're just parameters. You can think of them any other way you like. Okay, so I'm going to talk now about how to create parameterizations in general. This is a lot like parameterizing curves in that there is no single way to do it. There's just various tools. And again, one of my favorite metaphors, what we do very often in classes is we don't just teach you the way to do it. We give you tools for your toolbox, and who knows which ones are going to be useful at what time, right? So don't think of any one of these examples / methods that I'm going to show you as being the way to do it. They're just a way that works in some circumstances, and you have to kind of make the right choice in any given circumstance. Okay, so I'm going to start off with the easiest and my favorite and the most broadly applying, desert island choice of a surface parameterization method. I choose this one, the graph parameterization. Very natural. It's very much like the curve graph parameterization method that we talked about back in chapter 2? Early chapter 2? I forget. Anyway, we've talked about that before. If you have a graph, said differently, if you have solved for one of the rectangular variables as a function of the others, I emphasize you cannot always do this. Not every curve is a graph. But if it's a graph, and if you have solved for one of the variables as a function of the others, here's the move. The trick move, whatever are your input variables, let them be your parameters. It's just like with graph parameterizations of curves. The input variables, let them be your parameters. So let's see how that plays out in this example. Here, notice I have a graph because I've solved for z as a function of two input variables, x and y. So following the rule up here, with x and y as my input variables, I'm going to choose x and y to be the parameters s and t. That starts off our parameterization choice. Okay. And with that done, notice with x and y being s and t, I kind of don't even really have a choice as to what z is going to be. Z has to be s squared plus t squared. And everything has come together, and sure enough, I have now position as functions of two parameters, s and t. So, wonderful little method, highly algorithmic, pretty easy little algorithm at that, and fantastic tool for parameterizing surfaces. Okay, now notice the example that I did here. I had z solved for in terms of x and y. It's alphabetically kind of conventional, but of course there's nothing magic about alphabetical order. You can do any one you like. So for example, maybe sometimes it's easier to solve for y. Take this one as an example. In this equation here, if you wanted to parameterize this surface, whatever that is, what a weird surface, right? Cubics and exponentials, yikes. If you wanted to parameterize this, can you solve for z? No, you really can't, right? It's not like that, right? But it is, in this case, easy to solve for y. No problem. And having solved for one of the variables, in terms of the other two being x and z, we let x and z be our parameters. Whatever your input variables, let those be the parameters. Again, with that done, notice my sort of choice in how things go is basically done because y is already a function of x and z. X and z are now chosen, and so unavoidably I have to choose that for y. Everybody see how that works? Same idea. It's just kind of different variables playing the different roles. All right. You don't even have to restrict yourself to rectangular coordinates. You can use a morally equivalent idea in any coordinate system. So, for example, let's take spherical coordinates. And let's look at this equation right here. This is an equation in spherical coordinates. I have solved for one of the spherical variables as a function of the other two spherical variables. In fact, not only is this a function of phi and theta. This is a sufficiently easy function of phi and theta that theta doesn't even matter. Right? That's a good thing, not a bad thing. So, point is, solve for rho, and the only little tweak you have to apply to the method is that you have to, step one, write down the coordinate conversion formulas, and then, again, just do what you have to do. Notice, this formula tells me what rho has to be. I don't have any choice in the matter, and so plug that in for where rho is in those equations, and boom, parameterization. Right. Now, one difference in this method, you'll notice that I don't have a parameterization in terms of S and T. I didn't have to rewrite phi and theta as S and T because there's no confusion of variables as it stands, right? The outputs are X, Y, and Z. The inputs aren't X, Y, or Z. So there's no need to rename. I mean, look, if you really want to, you could rename them S and T. Feel free. That's fine, I suppose. It's completely unnecessary. So arguably more natural to leave it like that. So morally equivalent. This is what I would call, by the way, the spherical graph parameterization, because it's morally the same idea as a graph parameterization, just using spherical equations. How are we doing? Is everybody with me? Any questions? Cool. Okay, this next example. I'm going to go quickly through this next example. It's a little bit obscure, weird, manufactured. My main motivation for generating this example is I wanted to come up with something that was kind of a surface equivalent of a technique that we had back in when we were talking about parametric curves. And remember, one of the tricks that we had for parametric curves was how to deal with stuff like you have a bicycle wheel rolling down the road and the reflector, and of course that reflector makes a weird curve, and how do we parameterize that curve, right? And the big trick was use your knowledge of vectors. Sometimes position, that's a complicated curve, is actually a sum of simpler vectors, right? And so in those cases, use vector algebra. Try to write formulas for the simpler vectors individually, and then just add them up. Much easier. So here's my little manufactured weirdo example, and again, I don't want to get bogged down in this. This is not a super common thing to come up, but in the broad strokes, here's my surface that I'm going to start with, but that's not the surface I want to parameterize. What I'm going to do with that surface is I'm going to imagine that is somebody's top of somebody's head, and their hair, then they touch the electric static charge thing, right, and their hair, sticks straight out like this. And as a result of that, the ends of those hairs make a surface. That purple surface is what I want to parameterize. And how would we do this? Okay, so the big first idea is to recognize that points on this purple surface are actually much more easily understood as being points on the green surface plus these orange little vectors there. So it's going to turn out that the green surface is actually really easy to write down, to parameterize, that is. These orange vectors are actually not that bad to write down. And then green plus orange equals purple is all we're going to do. Okay, so let's take that one step at a time. What can I say about this green surface here? Well, let's check it out. It's a graph. Graph parameterization, done. Right, that green surface is really easy to parameterize. It just uses our previously discussed technique. So there you go. There's the green surface. Right, so now, though, let's try to understand these orange vectors. And very importantly, I'm going to have to reconceive of this green surface. I had previously viewed this green surface as being a graph. Right? Notice this equation here, written as a graph of a function. Very differently, though, it is also a level set of this different function. So I know flashbacks to early chapter 2 when we were talking about the difference between graphs and level sets and all that, and it seems kind of sort of much ado about nothing, right? It seemed kind of fussy, right? But remember, it's very important when you apply the calculus of level sets, you'd better make sure that you're applying it to the function whose level set is what you're interested in. And if you accidentally apply it to the wrong function, if you apply the calculus of level sets in the context of a graph, it makes no sense at all. It's absolute nonsense. Right? So very importantly, make sure you're very comfortable with this idea that we can rewrite the algebra just this little bit, and here now is a function whose level set describes this green surface. And cool thing then, I can talk about the gradient of that function. Gradients are perpendicular level sets. It's very important. This is the calculus of level sets that I'm using. It's very important that this surface be viewed as a level set because it is the calculus of level sets that tells me about this perpendicular gradient. And once I have that perpendicular gradient, notice that the orange vector that I want is just the normalized vector. So take that blue vector, divide it by its own magnitude. Boom. There you go. And so we're in business. Let me rewrite. Just gotta get rid of my mess here. So we have previously parameterized. Oh, whoops, wrong color. Previously parameterized the green surface, namely found those points. To that, we're going to add these orange vectors. And as planned, we can understand this outside surface as just being the sum green plus orange. So anyway, the little details that I glossed over quickly, you can check those details at your leisure. Come ask me in office hours if you have any questions about those details. But in the broad strokes, the point was this purple surface, hard to understand, can be thought of, points on that surface can be thought of as sums of simpler things. The green points are just easier. The orange vectors are easier. And adding them is easy too. Okay. All right, moving along. So here's a technique that is not obscure. This is actually pretty common. This is a really powerful technique. This might be my second choice. Desert island surface parameterization technique. And that is this idea of creating a new coordinate system. You'd be surprised how often this is actually really natural and really powerful. So just gonna dive in and let's consider this thing here called a torus. You've probably seen tori before. It's a surface of a donut. It's where the glaze is. So it's a surface, not a solid in particular. So how do we parameterize that surface? Okay, here's the trick. Again, we want to make a coordinate system. Now let's kind of think out loud here. If I lived on a planet that was this shape, right, how would I describe my how would we talk with each other about where we are on the surface of this torus? Think about longitude and latitude, for example, right? On planet Earth, do we describe our locations by our X, Y, Z coordinates? No, of course not. Hardly ever, right? We talk about our locations in terms of longitude and latitude. Certain angles, very naturally, sort of that makes sense in the context of the shape of the planet we live on, right? And it's just a natural and easy way to communicate about your location. So on this planet, what would be our natural sort of coordinates? And I would propose that we would do something like this, and this isn't the only answer, of course, but something along these lines. That we start off by looking at, I guess I'll use pencil here. So we'd start off by saying, okay, imagine some sort of an equator going around the outside. How much of an angle up above the equator do I have to go? Right, by what angle? Now, notice this is not an angle measured from the origin. This is an angle measured from kind of the middle of the dough here, right? The center of the circular cross section of dough, where we measure this angle that I'm calling T. And then the next angle that I would suggest is this angle right here, which you can think of as telling you by what angle do you go around the hole. And notice that's basically theta. So I would propose if we were living on this planet that S and T, which we might even call longitude and latitude, right? T is kind of suggestive of latitude. And S is really is kind of east longitude, right? But these coordinates, S and T, would be a reasonably, naturally convenient way of describing locations. I'm going to say we have created a coordinate system. Let me pause on that. Does everybody see how this coordinate system works? Okay. All right. So now, how does this help us with a parameterization? Well, with the coordinate system made up, all I have to do now is use geometry to literally find the coordinates of this point, and I just need to find the coordinates of that point now in terms of, well, S and T. So just a little bit of geometry. The first thing I'm going to do is think instead about this point right there. And I'm going to point out that that red point is this vector there, which is easy to write down. A, 0, 0. Easy vector, it's always the same. That vector, and now plus, let's see here, I'll use orange here. No, that's going to blend with the, let's see, I'll use blue. Okay, plus this vector here. Okay. That vector there in blue, which a little bit of trig will show has these coordinates right here. Now, this is something you do have to think through, and let me zoom so we can see it better. But if you look at this little blue vector, notice that blue vector, it's just, we know what its length is, right? And it's a constant, and then depending on what that angle T is, it just kind of rotates around in the XZ plane. And of course, this blue vector, being in the XZ plane, the second coordinate's 0. The first and third coordinates are just a little bit of trig. So nice exercise, good geometry exercise. Make sure you're comfortable with my assertion that that's this right here. Okay, you add those up, of course, and we get that for that red point. Is everybody happy? All right, so with that noted, thinking about that red point, now that I have a formula for that red point, keep in mind my actual goal is to find a formula for this purple point, and what geometric tools can I use to take my knowledge of this red point and figure out this purple point that you can tell is just, I'm literally rotating the red point around the z-axis to get to the purple point, and that's the giveaway. That's what we're going to do. We're going to think about how would I literally rotate in that direction around the z-axis. And that, of course, is a linear algebra thing. And rotations, counterclockwise, as seen from above, you might say, by an angle S. Math 218, linear algebra thing. So remember, the point is rotations are linear transformations. All linear transformations can be represented by matrices, and you can understand the columns of those matrices by just asking what are the images of the standard basis vectors. What does the linear transformation do to the standard basis vectors? That gives you your columns. That gives you your matrix. Again, if you're shaky on any of that stuff, come to office hours. I'm very, very happy to talk to you. Stick around after class today if you'd like. But make sure that you are solid on that, what I'll call Euclidean geometric linear transformations. Okay. All right, and we're basically done then, because we have our red point. We know how to do this green rotation, and then we just do it. Here's our red point. That was the first thing we analyzed. Here's our green rotation. And you can multiply that out. And that gives you this formula right here. And this is our parameterization of our donut. Okay. Everybody all right? It's a neat trick. Ultimately, now don't get lost in all the geometry of this, right? The point here is not so much the geometry. The point is that all of this became possible because we asked ourselves on this surface, how would I most naturally create a convenient, natural, easy to use coordinate system on that surface? And it is simply out of having decided what we wanted those coordinates to be, S and T, as I've drawn here, that was the foot in the door to then, I had to do some geometry. Sure. Right? But the foot in the door was creating the coordinate system, and then it's just geometry to get down to your answer. Okay. Really nice trick. Very commonly useful. Okay. Next example. Sometimes you have an existing, I didn't want it that in purple. Sometimes you have an existing parameterization already, or perhaps just something that's really easy to do. But what you want is not exactly that. What you want might, though, be an easily identified deformation of the easy parameterization. So if you know what the original surface is, and if you know how it gets deformed, then how does this play into the parameterization itself? So let's see an example. Here is what I'm going to call an existing parameterization, the unit sphere. Right? Easy to parameterize the unit sphere. After all, this is a spherical graph. So just straight up use the spherical graph parameterization, and that gives you this parameterization right here, written in vector notation, which if you prefer, you can write in coordinates as individual coordinate equations like that. Okay, so there's an example of an existing parameterization, something that's easy to do that arguably we kind of already had. Everybody with me so far? Okay, all right. Now here's the question though. What if what you want is to parameterize this ellipsoid? Now, this is a significantly harder problem. After all, while the sphere is easy to write in spherical coordinates, the ellipsoid is not, right? This is not just automatic easy formula. Rho is, I don't know, it's going to depend on phi and theta probably, depending on the A, B, and the C. It's really not clear how to proceed here. I don't have a spherical equation, so I can't use a spherical graph parameterization. I'm dead in the water. Anybody see the problem? Okay. So here's the good news. We know what the corresponding deformation is. The way I deform a sphere into an ellipsoid is just by stretching in the various directions. So, for example, notice here, given the equation of my ellipsoid here, you can see right here in the denominators, and think back to chapter 2, where we talked about how to interpret stretches algebraically and all that business. These denominators of A, B, and C tell me that where this ellipsoid comes from is that I started with the unit sphere, and then I stretched by a factor of A in the x direction, stretched by a factor of B in the y direction, and C in the z direction. Right? So we know now, let me color code again. We have an existing parameterization that was easy. Whoops, underlined. And I know what my deformation is. My deformation is stretches by various amounts in various directions. And that's going to be our foot in the door. Here we go. Let's think about it from the vector point of view. If I want to take this x coordinate, right? This is a formula for my x coordinate right here. This sine phi cosine theta. If I want to stretch by a factor of a, I want that x coordinate to be a times as big. Okay. no problem. There, I've made the x-coordinate a times as big by multiplying it by a. Right, the formula for x, I just multiplied it by a. And then likewise, the formula for y, I just multiply it by b. And the formula for z, I multiply by c. Just literally straight up stretch it out as we know we should. How do you feel about that? Is everybody all right with that? Okay, now let me take a different point of view on this. This is optional. We could, instead of thinking what we have in the first place as being a parameterization, I could think of what we have in the first place as being equations. And we have rules for how to execute stretches when you're talking about equations. The rules for doing those stretches is you replace, for example, x with x over a. So from an equations point of view, it's going to feel like we're dividing by a. From a parameterization point of view, it feels like we're multiplying by a. How come? What's the difference? When do you multiply? When do you divide? Well, you got to distinguish between, are we doing something to the coordinates themselves? Are we doing something to the equation, to the variables representing those coordinates inside an equation? Here, I'm taking the formula. Back over here. Here, I'm taking the formula for x itself. This is the formula for x itself, and I'm multiplying the formula for x itself by a. Whereas, on the other hand, over here, I'm viewing this now not as a formula for x, I'm viewing this as an equation involving x, and I'm replacing the variable x itself within that equation with x over a. And of course, ultimately, all of this is the exact same thing, because if you look at this parameterization over here, and this is x, y, z here, notice this equation is really the same equation as that equation. It's just that this a, I guess I've taken this a that's in the denominator and sort of cross multiplied it over here to the other side. It's really actually the same equation. So this is two different points of view on the same thing. It's not two different things. It's just two different angles on the same thing. So I hope that makes sense. It's a good thing to kind of stare at and digest. Let it sink in. Okay. All right. Okay. So we parameterized something by this deformation method, which if I had tried to go straight at it, I would have been in big trouble. Okay. All right. So last comment I'm going to give, there's a bunch of examples in the book, and they're fine examples. But they have a common shortcoming. And that is that all the examples in the book start with the parameterization and then ask the student to, hey, let's think through how to figure out what this parameterization represents. So they assume a parameterization and infer a surface. I believe that in reality, most of the time, in practice, day in and day out, it goes the other way. Most of the time, it's that you know something else about the surface. You know an equation for the surface or a geometric description of the surface, something like that. And what you need is to be able to create the parameterization. Totally different process, right? So what I want to point out is that even though the book does have some nice examples in it, they're all kind of, in a certain point of view, they're all kind of backwards. They assume their conclusion in a way, right? So perfectly fine to look at, but notice that all of my examples here are, I guess except for the first one, most of my examples here go to the question of how to create parameterizations, not how to interpret parameterizations. Okay. Alrighty. So, neat idea. I think this is very clever. Given a parametric surface, keep in mind, parametric surface gives you position x, y, z as functions of two parameters, s and t. Kind of an innocent observation, but if you were to fix t, right, let's nail down t. T is not allowed to change anymore. Well, if you think about it, if it's not allowed to change, it's not really a variable. Right? So what remains after I fix t is that I have position as a function of, well, ultimately really only the one variable, just s. T isn't changing. T is constant. So if you have position as a function of one parameter, keep in mind we already know what that is. That's parametric curve. Anytime you fix a parameter on a parametric surface, what you get is a parametric curve. Okay, let's see some examples, and by the way, vice versa if you fix the other one. So here's an example: parametric surface, unit sphere. We talked about this one before. Spherical graph parameterization. Right, rho equals 1. Make sure you're comfortable with where that came from. And let's look at some curves, coordinate curves. I'm going to start by asking what is the theta coordinate curve. And the way we're going to get the theta coordinate curve, by the way, we're looking at this point right here, where phi and theta are those values. The theta coordinate curve is what you get when you fix phi. Right? So I'm going to fix phi as being pi over 6. Phi is not allowed to change. It's stuck at pi over 6. Said differently, we are stuck on this cone right there, defined by phi equals pi over 6. Now let's ask the question, well, what happens on that theta coordinate curve when theta starts to change? Right? Theta is still a variable. Theta is allowed to change. And as theta goes, from some smaller value up through pi over 4 and continuing along, that just moves us around that cross section right there. So what I have there in blue, this is the theta coordinate curve, because phi is constant. Everybody good? Just an example. Let's do the other one. Let's consider now the phi coordinate curve. What does the phi coordinate curve look like? Well, the phi coordinate curve comes from fixing theta. Right? So I'm going to consider theta fixed. What does it look like when we fix theta? Well, geometrically, there is a theta plane. Right? And with theta fixed, now let's ask the question, what happens as phi varies? And as phi varies, well, we just sort of move down the sphere along that cross-section for that fixed value of theta. So that's what the phi coordinate curve looks like compared to the theta coordinate curve. Is everybody on board? Questions? Okay. All right, so why do we care? What's this good for? It turns out this is going to help us compute some stuff that I'm just going to work toward it. I'm going to leave the conclusion as a sort of a unexpected, surprise benefit, right? So first observation I want to make, though, and we'll get to what to do with this in a moment. If you take a partial derivative of a surface parameterization, I claim what that is it's a velocity vector of one of these coordinate curves. Now I want to talk through why that is. Velocity of a coordinate curve. Well, here's the idea. Step 1. What are these curves anyway? Coordinate curves. Well, a coordinate curve comes from fixing one of the inputs. Setting one of the inputs equal to a constant. Oh my God. That's exactly what we do when we take a partial derivative. We fix one of the inputs. Right? So coordinate curves, defining a coordinate curve in the first place, is the exact first step of taking a partial derivative. Now, how do you get a velocity then? Well, by a velocity, we take the derivative with respect to that input variable. Well, taking the derivative with respect to the other variable is the next step in computing a partial derivative. So just step by step, looking at a velocity of a coordinate curve is literally the process of taking a partial derivative of that surface. So that's just a convenient little observation to make, and that allows me to write down the following. If I want to look at this expression right here, x theta d theta. What is x theta d theta? Well, this thing here, x theta, is a partial derivative. That's what the subscript of theta means. It's a partial derivative of our parameterization, which means that it is a velocity vector. And if you think about it, a velocity vector is what you multiply by an input differential to get the corresponding output differential. So nice observation then that this little formula, x theta d theta, gives you an output differential, and specifically an output differential that corresponds to this d theta input differential. Let me pause on that. What do you think? Everybody all right with that? This is just saying velocity times time gives you displacement. Okay. All right. So then, likewise, there we go. Likewise, in the same way, this vector here is x phi d phi. So we've got nice little handy little compact formulas that tell me my output differentials corresponding to my input differentials. Now, this is a circumstance we've kind of seen before, sort of. Let me sort of redraw all of this, corresponding to an input differential d theta. Here's our output differential, x theta d theta, corresponding to our input differential d phi. Here's our output differential x phi d phi. Right, we've got formulas for these purple and dark blue vectors, and so then in fact, really, if you think about it, we now have a geometric relationship between this little differential piece of area in the parameter space and this little differential piece of area on the surface. Right? So I have a pretty explicit relationship between this green area and this blue area. And in fact, I can write that down precisely, because this blue area here is a little parallelogram. Yeah, close enough. It's not exactly, right? The surface is curving. These approximations in the limit, round off errors go away, all that as you would expect. But this output piece of area is basically a parallelogram. The area of a parallelogram in 3 space is an old formula from, again, Math 218 or early Math 219, how you want to think about it. It's the magnitude of the cross product of the edge vectors, and we already know those edge vectors from last time. So that is that little purple vector there, and this is that dark blue vector there. So, handy formula. And it's going to simplify even more, because good news, we have scalars in here that we can factor out. This d phi scalar, whoops, missed. Oh, no, that's it. There you go. The d phi scalar pops right out. The d theta scalar pops right out. Now let me rewrite the formula with all of that considered. And our output area is equal to now this thing, magnitude of a cross product of the partials, times this input area. Right? And this is exactly what we didn't really know we were aiming at this, but come to think of it, what we have inadvertently produced is a formula for a stretching factor. Thinking of the parameterization now as something that takes these little green input areas, and by way of the parameterization, contorts and distorts it around to produce this little piece of blue output area. The stretching factor of area, what do you multiply by green to get blue? There it is. It's this little thing right here. So, wonderfully convenient. We've inadvertently found our area stretching factor. Here it is, area stretching factor. Now, one thing that I do want to point out, this is just a notational thing. This vector here, the cross product itself, is actually useful for more things. This cross product, XV cross X theta, or in general, XS cross XT, the product of the partials of the parameterization, is interesting in other ways. So we need a name for it. I'm going to call it capital N as such. Notice then my formula for my stretching factor streamlines very nicely, and it becomes just the magnitude of capital N. Okay, how are we doing? Everybody on board? Okay. A little terminology thing. I call this the parametrized normal vector because, after all, it is a normal vector that comes straight out of a parameterization. Right? I mean, if you look at this thing, where this capital N comes from, it comes out of partials of X, the parameterization. So I like to call it the parametrized normal vector because that's where it comes from. It seems very natural to me. The book gives a different name to this. The book calls this the standard normal vector. It's terminology, right? It's just terminology. What I am uncomfortable about with that terminology is, to me, when you say standard normal vector, you do have to interpret that carefully because it's standard to the parameterization. It's not standard to the surface. You make sure to distinguish between the underlying surface itself versus the parameterization that you're using for the surface. Because there are lots of parameterizations. Each parameterization will give you a different capital N. I just think it's weird to have a bunch of different capital N's and call them all standard. Right? So anyway, whatever. It's just terminology. Anyway, there you go. Okay, how are we doing? Pausing again for questions. All right. So we're in business. Let's compute an area. I'm going to compute here the area of the unit sphere. Now, stylus, we already know the answer to this question. The goal of this example is not to compute something. The goal is not to get an answer. The goal is to see our tools in action, right? And by the way, the fact that we know the answer actually makes this a better example, because then when we get the answer that we know is the right answer, that's some sort of satisfaction that our methods and our tools are working correctly. It's a check. It's a, Anyway, so here we go. Unit sphere. Here's our parameterization of the unit sphere. Again, we've used this several times today already. This is the spherical graph parameterization from rho equals 1. Okay, now in order to compute our capital N vector, apparently I'm going to need to know the phi partial of x. So, all right, you got to take that phi partial of x. A little bit of calculus. Y'all can check the algebra on that. Notice I'm also going to need the theta partial of the parameterization. So you do the theta partial. You get this thing right here. And cranking out that cross product, the green phi partial cross the blue theta partial, and you cross that on out. And by the way, there's some Pythagorean identities that show up in the process of doing that cross product. This is a healthy exercise. Everybody should do this. Just so you've been down this road once before. I think it's a good road to have gone down. It's a very standard calculation. Side note, this did make an appearance one time on an exam 3. I don't remember how many years ago, but this calculation confirming that, that your capital N vector is this. So again, good exercise. Everybody should give that a try. And it's just trig and trig identities, and this is what you get. Now, of course, the stretching factor is not just the capital N vector. It is the magnitude of the capital N vector. And so, well, cranking out the magnitude of this thing is another Pythagorean exercise, right? So again, it's healthy exercise. Everybody should do it once in their lives. And your turn. Give it a shot. It'll take you 3 minutes. It's good exercise in making sure you're good with trig. And look how wonderfully it simplifies. It's just sine phi, and that makes this resulting integral really easy. Area, the whole is the sum of the parts. Each little piece of area is stretching factor times d phi d theta. The stretching factor we just computed. And that gives you then an easy integral and gets us to the correct answer that we knew we had. So there you go, 4 pi. Okay, good stopping point. We will call it a day here. Y'all have a great weekend. See you on Monday. And as usual, don't forget to stick around and make sure I mark you as present.